Hello, welcome back. I'm Munib Siddiqui and I'm a computer vision engineer. I did my bachelor's and master's in computer science and engineering with a particular focus on machine learning and deep learning. In this video, I'm going to show you how to train YOLOv5 on a custom dataset. We're not going to touch with the network architecture, but you can reconfigure the network architecture as well. So the main focus of this video would be how we prepare our data to train YOLOv5 on our own dataset. I'm going to use Google OpenImage dataset. I download some data and then I will show you how to prepare the data before you train YOLOv5. I'm not going to details of the network architecture or because this video I'm going to keep this video short, so I'm not going to go for the details of the YOLO network architecture, but I can just give you a little bit of information that YOLOv5 is a well-maintained repository on GitHub. So there are different models you can use it, from very small model to very a big model for object detection. Of course, there is a trade-off between a small model and big model in terms of speed and accuracy. It means the small model would have has faster inference, while the less accuracy, and the heavy model has better accuracy but a little bit lower inference. So in practical scenario, you would have a little bit delay on your FPS. Let me see. So to train YOLOv5 on your custom dataset, the first thing you need to do is to come to the YOLOv5 repo, which is Ultralytics YOLOv5. In here, you would find enough information about the YOLOv5. It's very well documented, and you'll get almost anything that you need to train this network on your local machine. As you can see, first is you need to clone this data, which I have already done, so please do it, and then switch to the YOLOv5 repository after cloning. Then you need to create a virtual environment using Conda or the pip virtual environment, and then install all the requirements in that environment. And when you're using PyCharm, make sure that your environment is actually set up for this environment that you have just created. It's always good practice to separate your environments or virtual environments for each project, because it will avoid some of the conflicts among dependencies. And then if you want to use the YOLOv5 on your own, like the pre-trained YOLOv5 without any customization, here is the just like 4 lines of code and you can use it. But remember that YOLOv5 is trained on Cocoa dataset, so you would have around 80 classes. All right, that's all for YOLOv5. A little bit information on OpenImage dataset supported and provided by Google. In here, if you come to if you just type OpenImage dataset on Google, you'll find this, and then if you type the name of the object that you are interested, you will get example images with bounding boxes, segmentation, and localization. So if I click the segmentation part and then choose the category of tomato, I'm getting the segmentation for this tomato. There is a command line that you can use to download the data, whether you want to download it into like only the images or the images with the annotation file. It's all up to you. If you have your own data set, whether like downloading this data and using that, and if you want to annotate that data using a free tool, please check out another video of mine called Label Me. By using the Label Me, you can annotate your own dataset. And the good thing about Label Me is that while you're annotating your data, it automatically annotates your data according to YOLOv5 input data format. So you will not need the steps that I will use to convert this annotation into YOLOv5 format. I think it's enough talk for the theory and a little bit information on the dataset. Let's jump into code and see how we can prepare our data. So basically I downloaded 4 classes of images from openImage dataset. In here I just want to show you a few examples of images from binoculars. I'm just going to delete these images because they're going to create problems later on. They're not true images, so it's like cached. So we have the binoculars images, as you can see in here. And I have another class of mango. We have the images of mango. And I have the images of tomato. And finally, zebra. So these are the 4 classes that I'll be using for this project. And for each class and each image we have Pascal format data, which is stored into XML file. There are some important information in this that we need to use that to train our YOLOv5 model, and that is the image name, the width and height of the image for normalization, and the binocular, the bounding box of the image. So this image is basically the annotation file in here is in the form of Pascal dataset format, which we have the xmin, ymax, ymin, and ymax of the bounding box. However, the YOLOv5 format needs something different. Pascal gives you the min of xy and the max of the xy, but YOLO needs the center of the object, the center coordinate of the bounding box of the object, and the width and height of the bounding box, and it has to be normalized along the x and y axis of the image, which is in here. So in this example we have 2 objects, which is person, and then we have tie, and then as you can see in here, this is the bounding box for the first person, which is Zaidan, and then we have another bounding box for this person, and then we have the center coordinate of this bounding box, and then we have the height and width of the bounding box. Similar for this object, and finally similar for this object. So we need to convert our XML file into a file similar to this one. To this one. In here we have the class ID, which is an integer referring to the class name. In this case, class ID 0 refers to person, class ID 27 refers to tie. And then we have the X center. The X center shows the center point of the bounding box, and the center point of the bounding box on the x-axis, and then the y center shows the y center point of the bounding box. And then we have the width and the height of the bounding box. As you can see, numbers are normalized, which means that they're in the range of 0 and 1. So we're going to normalize the annotation file and make our data ready, and then give it to the YOLOv5. So how are we going to normalize how are we going to convert our data from XML to YOLOv5 input data format? There are scripts available online. There are different types of coding you can use. I do it in 2 steps. First, I want to extract information from the XML file into programming, like in a programmable fashion. And then I'm going to store this extracted information from each file into a separate folder and change the XML suffix to .txt. Alright, let's do it. To read the XML file, just please structure your program like this. The code is available, you can download it and run it onto your machine to check. We are going to use openCV, so import the packages, and this is the package which is very important in this case to parse the XML file. We have the Windows name to preview our images, and finally we have the class name to ID mapping, which I showed you before that for each class we have an ID. So in this case I'm going to give it an ID of 0, 1, 2, 3 for binoculars, mango, tomato, and zebra respectively. And then to show you, I don't want to confuse you with the number of files in here. I'm just going to choose one file, XML file from here, and then I want to do the conversion and the reading everything on this file, and then I'm going to put it into a loop, and then so that the program will deal with each file. I'm going to, so this is the file that I have, XML file again, and this is alright. In here I have this XML file, and then I'm going to convert this. I'm going to extract information from this, and also I have the driver program to check each method that I create in here. Again, I'm going to tell you that you can build your own code for this. You can use a class to develop the code, or you can just create separate functions. So it's all up to you. It's okay. The point is to solve the problem. I'm going to define a function to extract information from this XML, and then I'm going to give it an XML file as an input. I call it root, and then from ET I call parse, and then I give the XML file to this parser, and then get root. So we're going to extract the information from this XML file first, and it has to be in a dictionary format, so I'm going to initialize the dictionary, info dictionary, and then I'm going to well, one of the elements of this dictionary will be the bounding boxes. I'm going to initialize it with that one as well. Bounding boxes, and then this is going to be a list of bounding boxes, because in each image you will have in some of the images you may have more than one bounding box, like let's say there is 2 zebra in one image, so you will have 2 bounding box for that. And the next thing is I want to loop through elements of this XML file here. So I want to loop through these elements in root, and then check the tag if element dot tag equals to. Okay, first let's get the file name from this one. We have this file name, so I'm going to check the tag for the file name. So I will call it file name, and if we get the file, if the tag of the element equals to the file name in that XML file, then I'm going to store it into the info dictionary. So I'm going to say the key of this info dictionary will be file name, and then element dot text. In here we use the text. So element dot text will return a string, and that is going to be the string, which is the file name of this, which is going to be basically this one. Next, I'll say else if element dot tag equals to. So next, let's check the size, which is the image width and height and the channel. So I'm going to use the size, and then I'm going to create so I'm going to store this size into a list, which is the first index would be the width and height, the width, and the second index would be the height, and the third index would be the channel of the images. Let's do that. So I'm going to create an image size, a variable, and then loop through each element, which is basically, I'm going to convert that. So let's do it like this. For sub element in element, and then I'm going to get that sub element and then convert it to integer, since it's going to be text integer sub element for sub element in element. And since we're going to get the value of this, I'm going to use the text. So that's it. And then let's save this into our dictionary that we have initialized above. I'll call it info dictionary, and the key of this would be image size equals to. It's always best practice to store your like to convert your list to tuple, because tuple is a little bit faster than the list, so just convert it to tuple, nothing more. So we use the tuple, and yeah, so far we got the file name and the image size from this XML file. The third information that we need to get from this XML file is the bounding box, and also I want to get this the name as well, so the class name and the bounding box. Let's do that. So we say else if element.tag equals to, so we have object, I guess, yeah, the tag is object. If it equals to object, then we're going to create a bounding box variable, a dictionary of bounding box, and then we're going to add each element separately into this dictionary. So let's check for sub elements into this element, because we have sub elements. So we call it sub element in element, and if this sub element dot tag equals to name, which is basically the class name, then we're going to add the bounding box. We call it class equal to sub element dot text. Else if, so we got the sub element name, which is this one, and then we're going to check the B and D box. Else if sub element dot tag equals to B and D box, which is bounding box. Then we have another loop, so to get that xmin, ymin, xmax, and ymax. So this has to be double equal. Then we're going to check the sub element. So we're going to say for sub element in sub element, and then we are going to store that into, let's get the tag dot tag, and then we are going to get each xmin, ymin, xmax, and ymax. So I'll get a sub element sub element dot txt, and since the dot txt returns a string and the value are integers, let's convert it back to integer. And then we need to add this bounding box dictionary into our top level dictionary. So we say info dictionary, and then we call it bounding box bounding boxes, and then equals to bounding box. Yep. So that's all for extracting this XML file into a little bit like readable format, I would say, or programmatic way readable, and then we're going to return that. Finally return the info dictionary. Let's check it out, and then you will get a better understanding of how does it look and why did we do that. I'm going to print it right away, extract info, and then I'm going to give that XML file path here and run this. All right, so yeah, this is the information that we needed to get from the XML file. We have a dictionary that the first key of this dictionary is another dictionary, and the first key of that dictionary is the class name. We have the xmin, xmax, ymin, and ymax. And then we have the file name, which is pretty necessary to get to save it and convert it. We want to save each file according to the file name that we have. And then we have the image size, which is the width, height, and depth of the image. So this is the step 1 we created. I'm just calling it a step 1. Step 1, extract XML info. And in step 2, what we need to do, step 2, we're going to save the extracted info into disk. So we're basically right now trying to convert and save it to the disk. So convert to YOLOv5 format and save the extracted info into the disk. So we're going to convert it and then save it to the disk. To the disk. Let's define our next function. Convert to YOLOv5. And then in here, what it takes as input is the info dictionary that we have just extracted. So I'm just giving the name as it is. And it's also good practice if you want to give it a hint, for example, saying that this is a dictionary or this is a string or how does it return. So for the next videos, I'm going to use that to make Python a little bit more readable and understandable from a programmer perspective. And all right, so now let's assume that we got our info dictionary, which is something like this. Now let's first loop through each bounding boxes that we got, which is this one, BB box. B boxes. So we call it for B box in info dictionary B boxes, and then try to find let's convert the classes into its respective IDs. We have this class name and we want to convert it to their corresponding IDs. Try. And it's also kind of sanity check to make sure that we have the classes that we already defined. So we say class ID. And then we have class ID to map. And then we give it the bounding box that we have taken, and then we, from this bounding box, we give the class name. Yep, that's it. For each try we need to have an exception, and that will be key error. And if this happens, we say invalid class must be one from let's say class name ID to mapping dot keys. Yeah, so we got our class ID. First step. Second step, what we need to do is to transform this bounding box. In here we have this bounding box as a format of xmin, max, ymin, ymax to change this into xcenter, ycenter, and bounding box width and height. Let's do that. Transform bounding box into YOLOv5 format. So I'm just writing x center y center, and then we have width and height. All right, let's just call it box x center. I'll call it b box x center, which is bounding box, and then it's a little bit more intuitive, b box y center, and then we have the bounding box width, and then we have bounding box height. So we get we're going to add up the bounding box xmin plus bounding box xmax, and then we are going to divide it by 2. What is this? You are not welcome here. Alright, and then we divide it by 2. And then we have the bounding box, which is pretty similar. So let me just copy paste this. Control C, Control V, and then I'm going to change this to Y, and then this one to Y, and that's it. For finding the width, we need to do is to get the bounding box, this one. I'm going to copy paste this. Xmin, basically it has to be xmax minus xmin. And to find the height, we are going to have ymax and then ymin. Yep, that's it. We converted our bounding boxes to from xmin, ymin, xmax, ymax to the format that is required by YOLOv5. And then the next step is to normalize it. So let's say normalize the coordinates by coordinates. Normalize the coordinates along the along the width and height of the image. And it's easy. All we need to do is to get the image width, image height, and we don't need the channel, so I'm just putting it at dash, and we get that as well from the from the info dictionary. So in here I'm going to write info dictionary, and yeah, it has to be image size. And then we are going to normalize the bounding box center, which is basically this one divided by image width divided by image width. Yep. And what I'm going to do is to get a duplicate of this, and then we have y, and then this has to be height, and then I'm going to normalize the width and height. So let me just width divided on width, and then we have the height divided on the image height and stored back into the bounding box height. So we did that normalization as well. If we come back to the format before, we finish with the format. We got the class ID, we normalize our image, we convert the image, the annotation, the bounding box xmin, ymin, xmax, ymax into bounding box center value, the bounding box width and height, and then we normalize it onto in the range of 0 and 1 along the image width and height. Let me come back. So the next step is we need to save this into the disk. To do that, well, there is I'm going to create another function to do that for all the images and annotation files. For now, I will just make things simple. All you need to do is to create a folder in here, new directory, and then give it the name annotations, and then we have these 4 classes, right? We have create these 4 directories as well. So we have binoculars, and then we have mango, and then we have tomato, not a Python directory, simple directory, and then we have zebra. And then in here just address those classes and save it. So I'm going to use print to save this file, so I'll create a print buffer in here. Print buffer equals to a list, and initialize the print buffer with a list, and let's say print buffer dot append, and then we have this 5 information, like 5 pieces of information. We have the class ID, we have the bounding box x center, y center, and width and height. So I'm going to create 5 of this and then reformat it. Let me give it a space. Our first is going to be the, let me format it. So the first piece of information that we're going to put into print buffer is the class ID. Then we have the bounding box x center. The order is very important, by the way. Bounding box x center, and then the bounding box y center, and then the width. As I told you, the order is very important, so we're going to check this again. We have, yeah, so we have the width and then the height. Alright, the width and the height, bounding box height. In here, let's make it that we want to store only the up to 3 digits of the floating points. 3 digits of the floating points, up to 3 digits of the floating points, up to 3 digits of the floating points. And then let's save it. So we're going to save it into each file that we have created. So I'm going to give it a name, save file name, and there's going to be ospath.join. We have this annotations, and then we have this info dictionary, and then from that info dictionary, if you remember, we got the bounding boxes, so I'm going to say the bounding boxes bounding boxes, and then we get the, alright, since we are using single quotation inside, let's put double quotation, so the single quotation would be treated as a string. And then we have, from here we get the first element, and from the first element of dictionary we have the key called class. Let me get that key as well. So class. So what it does basically, it takes us to annotations, and there's the class name. Because I'm going to structure it in a way that we can use it later on in our loop. So I'll make sure that it should work automatically rather than like typing it by myself. And then, yeah, I'm going to get that, and this is going to be the first element, the first parameter of this, and then the second one would be info dictionary, getting the file name here, file name, and then from the file name I'm going to replace, by the way, why we get this? Okay, I think we're okay to go ahead. Let me just do it this way. Yep, I think we're fine to go. Alright, replace replace XML with txt. I'm going to use it later on for the image purpose, so I'm going to call it replace JPG to XML. Since the file name in here is actually a JPG file, yeah, we have this JPG, and I'm going to replace it to txt and then store it. That's it. We're going to save it. So let me save this .join, and then I'm going to just join it with the information that we got from the print buffer, and then we have file. I'm going to open that file that we just created. Save file name and write it, and then return a message, also print out a message, saved, let's say saved, let's say save successful. Keeping it simple. Alright, so again, to summarize it, what we did in here, we got our dictionary information and give it to another function called convert to YOLOv5. We are going to get the class ID. We transform the bounding boxes into YOLOv5 format, which is the bounding box center value and the width and height. And then we normalized each value of the bounding box along the X and Y axis of the image. And then we save this information into a file and save the file into the disk. And we show a successful message. In here, I'm not going to print it. I'm going to store it into a dictionary, into a variable. And then I'm going to convert it to YOLOv5. So convert to YOLOv5. Convert to YOLOv5. Let's see. Hopefully we are not getting. Hopefully we do not get any error. YOLOv5, and I'm going to pass the info dictionary in here. Let's say the string indices must be integers. let's see that. Let's see how we can solve it. Let me turn on the debugger in here and then debug it. What's the information from the bounding box that we get? Okay, so we have the bounding box equals to the class, and that's not what we need to get. So basically I think the information is the problem is caused by this function extract info. So we have the bounding boxes that we created in here. We have we added this bounding box into this bounding boxes, and then if you come here, alright, so we have a list in here, and then we equal that list to that bounding box, which is not correct. We gotta append it, each bounding box, into that list. And hopefully it works now. Let me rerun this debugger one more time and see. Okay, now we have gotten our class, which we need the binocular, the class name, in this case binoculars, and then we get the x-min, y-min from the bounding box. I think it should work now. Let me rerun it. Oh, my laptop. Yeah. Save successful. If we come here, and this is the text file that we got the class ID, x center, y center, and width and height of the bounding box. That's it. And the next step would be to do it for the all data that we have. Let's do that part as well. Before we go to generate all this data and then convert it to their respective an annotation file, before we do that, let's do some sanity checks, which is to make sure that each bounding box corresponds to each annotation that we have just converted corresponds to the correct bounding box on the image. To do that, I'm just going to create another function called draw bounding box. And then we get the image and annotation text file that we have just converted. So I'm going to open that file with open annotation text file as a readable file, then annotations would be annotations equal to file.read, and then split the space that we have in the file, each line. If there are more than one line, like if there is two bounding boxes on the same image, and we're making sure that we get it from all the lines, as many bounding boxes that we have, we gotta split that and then store it into annotations. And since we are using with single file in here, let me just call it annotation, and the second step is to create it. So let's see, for x in annotation, x split let's split the space from the annotation file as well, and then annotation equals to for y in for x in annotation again. And then we will have another list in here for y in x. And then convert this annotation value into float. So we loop through the annotations, which is the line that we have, and then for each annotation, like the xy, like the value that we have, we want to make sure that all the values in float format, including the class ID, it's okay. So we convert this to annotations to a NumPy array. So basically it has a form of again something like this: class ID, we have the x center, y center, bounding box width, and bounding box height. Yeah, and then so let's just if you would like to know that, you can just print it, but I'm just going quick. So let me get the image width, height, and channel from image shape that we get, so that we can denormalize our annotation files. Denormalize. Let me print this so that you'll understand better. And we have annotation value before annotation values before denormalize, before denormalization, and then we have this annotation here. And then we are going to denormalize, which is basically getting the actual XY and image bounding box width and height coordinates on the actual image. So we're going to denormalize the value that we normalize it during conversion. So denormalize, and that is denormalize annotations. So what we need to do is to denormalize it, we need to get the let me just keep a copy of this. Annotations copy, NumPy copy annotations, and then annotation copy. So let's go through all the rows that we have, and then we get the x center and width of the bounding box. X center and width of the bounding box, and then we're going to denormalize it. So basically, to denormalize it, we are going to save it into annotations. Again, all the values, all the rows, but only x center and width of the image. So we're going to multiply it by the image width. And similar to this, we are going to have we have a problem in here, and that says that annotations we have these annotations, the values from 1 to 3. Okay, first index and second index, and then multiply it by width. And then here we have the second and last index, and then multiply it by height of the image. And this has to be 4, and this has to be 2 as well. So in here we're going to denormalize the X center and bounding box width, and in here we're going to denormalize the Y center of the bounding box and bounding box height. So the denormalization done, we can print it out if you're interested. Annotation value after denormalization. Normalization. And this is the annotations CP. So we did denormalize our value to make it suitable for openCV. All we need to do is to convert it back to min-max value, similar to the first value of the annotation boxes. To do that, we let me do one thing. This shouldn't be in here. Okay. Yep. And to do that, what we need to do is to convert our annotation values from X center, Y center to min-max values. Let's convert it back. Convert to xmin, ymin, xmax, ymin, and ymax. Ymin and ymax. To draw what? To draw cv2.rectangle. So to do that, we need to get the annotations. First element of the annotation CP, and then we say annotation CP the first element minus annotation CP, the third element, and then we are going to divide it by 2. So what we are doing in here, we try to find the minimax for each annotation. So we're going to convert each element into minimax for the X and Y of the bounding box. And to do that, we get the first element of this annotations, and then the third element from this annotation, which is the X center and bounding box width. So I'm going to the center minus the width of the bounding box. So we have the center minus width, and then we are going to divide it by 2 to get the rectangle. And then, so it's like this, you are getting the minimum value. So we get the first element, and then we're trying to like you get the first element and then you convert it to minimum value, and then you get the second element and then you convert it to the maximum value. So we do it like that. And then we're going to copy this 4 times. This has to be 4 and this has to be 3. It's okay, and this has to be 4. I'm just doing it quickly. You do the calculation, it's pretty easy. This has to be 1 and this has to be 2. So what we are doing, we're doing the opposite of this one. We're doing to transform the bounding boxes into back openCV format. And then we are going to draw each annotation box. So let's do it, and we don't have this 2 in here, and also we don't have this 2 in here. So to draw it, we come and say for single bounding box, for single annotation in annotation CP, object class, which is the class name. We have the x0, y0, x1, y1, which is basically the x-min, y-min, x-max, y-max, and we call it single annotation. We get it from the single annotation. Then cv2.rectangle. We have the image we got, and then we are going to use the values that we get. So 0.1 would be integer x, integer x0, and integer y0, and 0.2 would be integer x1 and integer x2, y1. And then we have the color, so I'm just going to give it a color 255 and 0 and 0. RGB color, so probably blue color, since OpenCV is working with BGR images. And then I'm going to use cv2 dot let me give it a thickness of 2, and then cv2 dot imshow. The Windows name that we create, that the constant name that we have in here, I'm going to use it in here. Windows name, and finally the image. Give it a wait key of 1. Delay, let's have a delay until we press the skip, and then once we press the skip button, then it has to destroy all the windows. Dictionary created, and then let's run it. So if you come here, it has to, file saved, and if we come to Zebra, we have this annotation file, and then I'm going to read that just for the sanity check purpose, to make sure that the annotation, the normalized annotation file that we have just created in the YOLOv5 format is working fine. And then let's run this and see. So as you can see, we have a problem in here. The annotation is not really like the bounding box is not drawn properly on the image. So what we're gonna do, we come back. I think we have a problem with the mix man. In here we get the first element. Okay, I think it has to be 2, 3, and 4. Let's run it again. this and rerun. Yeah, so the bounding boxes are correctly drawn on the image, so it's okay. Now it's working fine. The final step to make sure that our data is properly converted into, all of our data is converted to, I don't need this anymore. So the next step is to create a loop so that all the data would be taken from this image dataset, and each should be converted into their into the annotation file format of YOLOv5. Let's do that one as well. I'm going to create another function called data generator, and then I will call the function that we have just created, and then I'm going to call these functions into that data generator function. So to do that, let's define our function, call the data generator, and then this data generator will get a root path for the data, and the type of that has to be string, and I'm going to get the root path back root path, and then we get the annotation dirs, annotation dir, initialize it with a dictionary, and then we call for classes dir in is dot list dot root path. So in our case, the root path is basically the image data, so we are going to get the image data, and then we have these all classes. Okay, so we say if classes dir equals to there is a hidden file called ds store in my in here. If I list it out on CMD, there is a hidden file called ds store, so I just want to ignore that. If the class directory name matches to this file, to this directory, then ignore that, go back to the loop. And else we want to have our annotation directory, the dictionary that we initialized. We get all this class dir, and then we want to get the path.join. For each class dir, we want to add the path for annotation directories, which is here. So we get the root path, and then we join it with a string of classes dir, and then we have the Pascal class in here. So we have something called Pascal in here. We get the Pascal. Yep. We have I think I need to put it into a single quotation. Alright, it has to work now. Yep. And if you want to know the the file path for that, you can just take the keys for this one. Annotation keys, annotations dirs, and then annotation dir directory dot keys. You get the, so we're trying to get to this file directory. Okay, for each of these classes here. And the next thing that we are going to do is to get the class name for each of these directories. Let's do that for class name in annotation dir dot keys that we have just printed out. And then we are going to get the XML file for XML file name. I'm going to use bar to show us that we are going to read each XML file. So I'm calling this for XML file in tqdm dot. Remember that I imported tqdm above here. So if you just import tqdm, you can just use tqdm.tqdm, otherwise just tqdm is fine. And os dot list dir, and then we have annotation dir, and then in here we have the class name. And let's get the XML file path. XML file path is equal to ospath.join, and then we get the annotation dir class name, and class name, and then the XML file name. So that's how we read each file, XML file from each of these classes. That's all. And let me put a case if ospath exists. If ospath exists, dot annotations. So you know that we have this annotation file. Let's check if that one exists. Then we call that function extracted info. Did I just call it extract inf? Oh my goodness. This is info. And we're coming back, extract info, and then we give that XML file path, and we call this output as an extracted information, and then we pass this extracted information into our convert to YOLOv5 information. So let's do that. Convert to YOLOv5 and extracted info. If you recall, there is a print that I have created, so I'm going to remove that. I don't want to like have a lot of logs in here. And if this is not the case, then make dirs, or it should be like this. If this exists, do this, else create make dirs. I think I can do it in a better way. If not os exists, then os dot make dirs, create that, and then get out of the loop. So let's create the directory, which is in fact we have the directory, but in case we don't have it, so I'm trying to figure out that part. we're going to create a directory as the name annotations and then class name. Okay, we're going to create a number of directories and then extract info and then convert that. Yep, that's it. Else, we don't need this else. And we say XML2 at the end, just gives us a print XML2 YOLOv5 txt conversion successful. And then we call this function in our driver program. So let me just do this. Data generator, and then I'm giving it the path, which is the root path. So root path in this case is image data. That's it. And I'm giving it the root path here. So we have this files, and then we want to like create all these annotations and move it to this one. So I'm going to delete this. You can delete all of this, it's okay, it doesn't matter. So let's run this. Hopefully it works. Alright, so we actually converted XML to YOLOv5 conversion successful. But I don't know why we get this after the TQDM, which is here. It has to be printed at the end. Class name, and this one we have class name. Anyway, don't we have anything weird here? So if we come back to the annotation file, we do not have the files in here. All we need to do is to make sure that all the files are moved to the annotation file. So we have to do that. Let me just, if not exist, it works, but it exists, so it does not work. If exists, do that. If it does not exist, make dirs. If it does not exist, if it exists, if not always exists, class name, create dir. Okay, and then extract info and then convert to YOLOv5 and save it. I think this has to be here. Control X. Let me just bring it here. And then remove this part, and then it should work. Let me just try it again. Okay, let's check this part again. come into annotation folder and you'll have all the annotation files. And then you have the mango, and similar to that for the other one as well, for the tomato and zebra. So we successfully converted our annotations from YOLO, from XML to YOLO version. The last step is to split this data into train, validation, and test it. To do that, I'll just create a utility function called let's just like move these files to another folder. To do that, I'll just create a utility function called move files to folder, and then we give it a list of files and destination folder, and then we use for if in list of files try. We have the module called shuttle dot I can copy move, so for safety I just use copy for now, but you can use the keyword move so that I'm checking if it's working properly or not. If it works fine, then you can just change the copy keyword to move, except printf and say assert false. That's it. I think we don't need this part. I call it utility function to move files. And then I'm coming to the very last part of our conversion. So we need to create 3 folders by the name of test folder and validation folder and train folder, so that we can move our files to there. And we also need to make sure that our images are randomly shuffled, and while we are randomly shuffling the images, the annotation and image files should be matched to each other. To do that, we come to our driver program, and then we don't need to run this part again, so I'm just comment that out, and all I need to do is to split these images. So a split. Before that, let me just do one thing. So we need to get our data, and we need to get our images and annotation files. To do that, I'm going to create a data, initialize it with a dictionary. So this is going to be a dictionary, and then we have path to annotation files, and this is going to be a list, and I have path to image files. It's going to be a list as well. And then I'm going to read all the class ID in os.list dir annotation root. So I need to put the annotation root something, annotation root, which is basically our annotation files in here. So we call it annotation. It's annotation. Yeah, annotation root, and then we have annotation root in here, and we get the annotation class dir ospath.join. So we get the annotation root and the class ID, and we get the image class dir, which directory. We get the ospath join annotation. Okay, we can do that with image root, I guess. Image root, which is the root path. I call it, okay, root path. Root path. What do we have? Root path, and then we have the classes. So class ID, and if you look at that root path of this image, we have this images name. So I'm just putting it as images, and that's all. I have another loop to loop through all the annotation files, so I'll call it annotation file in os.list dir annotation class directory, and then I have to get the annotation path for each file, ospath.join, and then I'm going to get the annotation class dir annotation class dir, and then we get the annotation file. So we are going to, yep, annotation file, annotation path to annotation. It has to be annotation file, I think. Path to annotation file, path. I think this is annotation file, so I just don't want to like use words to confuse you. Annotation file, I think better to use single annotation file, and then we have the image path. So image path is equal to ospath.join, and similar to that we have image class dir, and then we have okay, let's get the annotation file in here as well. So annotation file, and then we replace the txt to jpg. That's it for our annotation files, and then what we need to do is to append this to our list that we have just created. So we say path to annotation files dot append, and then we get the annotation path. We give the annotation path in here, and then path to image files dot append mg path. So we store all of our annotation file path, which is in here, and images which are in here, and we store it into our list. And then what we need to do to split that, so let's split the image data into train, val, and test sets. And to do that we need to use the train split function of the sklearn scikit-learn. So I'm coming to we're getting the images, train images, and what will be the next one? Validation images. Let's make it plural images. And finally, and train annotations and validation annotations. And we give it as train split sit, so we get the path to image files in here and path to annotation files in here, and the last argument is going to be we give the path to annotation file and path to image files, and then we are going to specify the size of the train. So in this case I'm going to use size like 80, 10, 10, which is 80% for and 10% for the validation purpose and 10% for the test purpose. So to do that, we come to give a test split in here, 0.2 test size, which is actually validation size. Test size will be 0.2, and then random state 1 equals to 1. So that's it. And then from the validation part, we're going to get the actual validation. So I will call it val image. Val image and val and test images, val annotation and test annotation. Again, the same function we are using, train test split. In here, the only difference is that we're going to give it the val images in this case, and then the val annotation that we define above, so val annotations. And then test size this time will be 0.1, which means 10%, and random state no needed. I think we're going to divide it into two parts. Yep, so and random state 1. So we get our validation data, which is 20%, and we split it into 50-50%. To 50 would be for the validation and 50 would be for test set. So to combine it together, and from the total portion it will be like 10%. And there is a typo image, and then let's move our files. There is one thing I want to point out, and that is that in YOLOv5 all your images and data should be stored in an image and labels format, because the YOLOv5 model will search for image and then accordingly replace the image part to labels and then search for the corresponding labels for that image. and that's why we need to be specific with the name, so we can't really use another name for now. If you want to change or adjust the setting of the YOLOv5, for sure you can do that, but we're not going to complicate the stuffs. I'm just going to keep it simple. So files to folder, the utility function that we have created, and in here I put the train images, and then images, label folder, and the images into the image folder. Again, I want to emphasize that the images name and the labels should be like in this order. Like the YOLOv5 will look at this path and then change the images to labels to find the label for the corresponding image. Let's run this and check the result. Alright, if you come to the to each of these folders, we see that these are our images. If you come to, since I choose a random one, we have like images from each classes, like different classes in here. And similar goes, the same goes for the validation and also for the tests. And if you come to the train test, we have all these text files. That is, in here we have 2 bounding box for this image, so it shows 2 rows of data, and that's it. The next step that we need to take is to give this data into the network. So we're in the second step of, well, first step was data preparation that we did. Second step is to give this data to the network to train the network. So we're going to train the network. And the third step would be to test the train network. To do that, what we need to do is to create a YAML file and then place it into the data folder of this YOLOv5. In here we come to this and then right click and then specify file, and then we say custom custom dataset. I will call it YAML file. So let me close this. Let me delete this and create it again. In the data folder, create a YAML file and name it custom dataset.yaml. In this YAML file, what you need to do is to specify the path of your data, which is the train, val, and test. So we say train, and that is in where we have the train data. So it's in the images and train, and then we have val. So we go to a directory back and then images and then val, and then we have the test data, images, and test. In here it's important, again, like the YOLOv5 is looking for the annotation or the label of each split of the data by changing the images into the labels. So what we need to do is to specify the number of classes, call it number of classes, and C is 4, we have 4 classes, and then we give the class names. So we say names equal to, if you come back to our YOLOv5, the class name has to be in order of 0 to 3, which is 4 classes, so we gotta keep the order. We have binoculars, I'm just going to copy this and then coming here and then paste it and then remove the keys, the values. Let me just keep the keys. And since this is a YAML file, it has to be colon, not equal. And this one is path to dataset, data splits, which is train, val, and test. So we are ready to go to train the model, but before that, let me just go to some of the files in here. What do we have? If I open here, we have in data some sample images in here. We have the hyperparameters that you can use for fine-tuning. For example, if I come to this low model, we have this learning rate, final one cycle learning rate. We have the momentum, weight decay, warm-up, epochs, warm-up, bias, learning rate, boxes, and so on. If you want to like tune or play with these parameters, it's still okay, you can do that, but it's recommended to use the default one unless you change the structure of the network, which is you need to specify your own learning rate or optimization function. And this is for the in the beginning of the video I mentioned that YOLOv5 come in 3 forms, which is a small, medium, and large. So we have the low, mid, and high. This is the hyperparameters referring to small, medium, and large models. And in here you get the COCO dataset, which is the number of classes. And the reason I put that data as a custom dataset is I choose the format from here, and this is the number of classes and the names. So we did the same format, and we, instead of giving the COCO dataset, we're going to give the actual custom dataset that we have created. And this is a little bit more information. Different dataset we have, number of classes, SKU, visual drone that we can train it on. So that's how it is. And coming to the models, we have a YOLOv5 large, which is the structure. This shows the structure of the model. So we have number of classes 80, which is the COCO dataset, depth of multiple, and course. You can change that if you want to. Backbone, if you want to customize the backbone of the network, you can customize it in here. And this is the head, and that's it. So this is for the nano model, and this is for the small model, and so on. And in hub we have all these other parts. I think what we need to do is there's one more task that we need to. All right, let me check. So we don't need to go through that. We have some scripts in here to fetch the YAML files and basically give it to the network to train the network or to make the inference. What we need to do is to get the pre-trained weight and then train the network. Okay, let me just train this network. To train the network, you can do it. Okay, so it's here. Yeah, sorry. All we need to do is type Python and train.py, and then here you specify the size of the image, which is in my case it's fixed. You gotta give it a 640 by 640. So the image size is 640 by 640, and then from the configuration file we need to say the model. I would say YOLOv5. Well, I think we don't have the files available, so let me just check. I think we don't have the models. The models has to be in here. Okay, so YOLOv5 is small. Okay, what we need to do, get this configuration from models, YOLOv5, medium.yml, and then the hyperparameter, basically hyp, we get it hyp. So we have the hyperparameters in okay, sorry. Hyperparameters are in data, hyp, and then you gotta specify the hyp. So we are going to train it from scratch. Data hyp.scratch, and the next parameter that you need to specify is the batch size, epochs, and the data. So we say the batch, let's say 32, and then the number of epochs 100, and then the data we say custom data, and it has to be data custom data dot YAML. This part is very important. We are going to give we are going to give the custom data to the model, our own data to the model. And then finally weights. Unfortunately we don't have the weight setting, so that we can use some of the pre-trained weights. I think we need to download that. Let me just still check that. Weights, and then we have to specify the model weight. So if I come here, so let's check how we can find the weights. There is scripts. Okay, we have this weights. We need to run that. I'm going to open a new terminal, since I don't want to mess up with that one right now. So that's all. You can use it on there. It's okay. Conda activate YOLOv5, and then cd desktop YOLOv5, again YOLOv5, cd. Well, let's run it directly. We have it in data, scripts, and download weights. It's not a directory. I think we just need to do it this way. So these are the pre-trained weights of all the YOLOv5 models. If we come back here and check, we're getting some new files added up here, which are basically the YOLOv5 weights. So let's wait for a while it's indexing. Yeah, you get that right. There we go. We have these weights. We need to download that. Alright, we go back to our terminal and wait for a while so that it gets downloaded. Let's see. We have YOLOv5M. We're going to use that one. So I'm going to close this. And Then in here I'm going to specify YOLOv5 m.pt, and the next argument is the number of workers. I'll choose a 24, and then let's say the folder that it will create to save the base model for inference. To save that, we just specify it in here. Name, we say custom dataset train, or just custom dataset. I mean, I would just say custom log, and then enter. Okay, let's see. We're going to wait. It's going to take time to train that. Of course, I'm not going to train it on my laptop in here, but I just want to show you that how like it has to work, you know. Okay, we got something hyperparameter scratch acceptable suffixes .yaml, not .yml. Okay, I think we made a mistake in the hyperparameters scratch. Okay, let me just come to here. Scratch.yaml. Okay. Scratch.yaml. Well, I didn't train that on my laptop in here. I did train it in a GPU, and then I got the result back, which I'm going to show you right now. So training it on your computer will take you like 2-3 days, to be honest. But on a GPU, it will take like less than 30 minutes, less than an hour. And while it's getting trained, during training, get some coffee, take some walk, and then come back. We'll be back soon after training, and I'll show you the result. Okay. So we get the epochs, we get the bounding box, we have the label, image size, all the informations we get from during the training, and also the mean precision accuracy. So alright, so we trained the network, and then after training a new folder will be generated automatically. Come to that folder, which is called runs, and you'll have the train, and then you have the custom log that we defined during the model training setup. And in here you'll have the weights of the model. The base weight for this from this training is saved in here, where we use it for the inference purpose. While testing the network on the test dataset, you get a confusion matrix, which is basically showing you the parts that the model kind of confused, like which class. Well, basically, confusion matrix has its own like need a detailed explanation so that you'll understand, but I just want to give you a high-level understanding that whenever you go for the confusion matrix, just go for the diagonal part to see the accuracy of each model, each class. For example, for the binoculars, we have an accuracy of 0.50. For the mango, we have an accuracy of 0.42. For the tomato, we have an accuracy of 0.44, and for the zebra, we have an accuracy of 0.69. What does it mean? That it means that our model performs very well on zebra, then a little bit bad on tomato, and like so bad 42% accuracy on mango and 50% on binoculars. And there are classes where the model couldn't properly classified, or what are the classes that the model classified which were not actually to that class. So it gives us detailed information about the true positive and true negative information of each classes. We have the F1 curve. F1 curve also, please check it out online if you need explanation on this theoretical concepts. Write it down on the comment section below this video, so that I will prepare another video describing these scores. And then we have the hyperparameter that this model used, and we have the labels and their distributions. So we have instances, for example, for binoculars we have 50 images. For mango we have around less than 200. For the tomato we have a lot of images, 350. For the zebra around 200. And this is the correlogram for the labels, and this is the options that has been used. For example, hyperparameters, number of epochs, batch size, image size, rect if in case we use it, we didn't use the resume, bucket, and so on. This is the P and PR curve. Again, these needs to be explained detail, which is out of the scope of this video. But basically the PR curve is the R curve, or the PR curve is used a lot when we want to accurately thoroughly want to understand why the model is not performing well, or in which class the model is not doing well, which is very helpful if we want to improve the performance of the model. In here we have, for example, for the precision and recall of the mango, we have get a precision of 28, 29, and we get a very bad recall. So this kind of like intersection between precision and recall gives you the PR curve, which gives you quite detailed information about which class the model is doing well on which class, and the model is not doing quite well on which class. And this is the R curve. Again, if you would like me to provide another video on these concepts, which are very theoretical, please write it down below in the comment section, and if it gets enough vote, I will come to that and make a video about that. And this is the result for the training and validation. This is our train batch, just as an example, so that you'll get an understanding how the images were labeled. And this is another batch of the training. As you can see, the images are different images with their corresponding class ID. And this is another batch of the training. And finally we have the so this is the validation batch. In here we can understand like how well the model was performing during the validation. For example, this is zebra. Is it really classifying zebra as a zebra? And you can see that it's doing well. In here is zebra, and this is binoculars, and we have tomato in here, and in here the model is not doing quite well. In here it's doing pretty well, and so on. And this is the label, and this is the actual prediction. So that's it. And this is the training screenshot I got from after training, so that you can get an understanding of how that's the final outcome is going to be. We model summary, we have 367 layers, around 461 4,612, 46,124,433 parameters for this, which took 107 gflops, and we have the classes that we use for this, which are the binoculars, mango, tomato, and zebra. We have the number of images, labels, and then we have the precision and accuracy of each of this. So well, that's it for this video. If you have any you can use this weight to check to make inference on the test set. To do that, we just need to use the test or the detect part of so we train the model, we get the base and last weight of the model. What we need to do is the last step, which is the inference. Basically, inference means that we got the model. Now we want to give it just a test image and see how is the outcome. We don't have a label in here. I mean, for the test purposes, usually we don't need to have a label, and we are not going to give the model any label. And we want to see how the model actually works in real world. To do that, all you need to do is to come to the terminal and then specify this. To do that, all you need to do is to come to your terminal and then specify the Python detect source, the source of the images that we have, which are the image files, and then the weights, which are located in runs, train, custom log, weights, and based, which is in here. If we come, we have runs, train, custom log, weights, and based. So, and then we give it a custom log again, or we can say detect log, and this is going to be custom log or detection log, doesn't matter. Okay, let me just give it to detection log, and then run it. So now we're going to build the layers again and use the trained weights, and then give each image to the model, and then get the result back. Let's see how the model really does. So basically, where we have dedicated 57 images for test purpose, and we can test it. While it's running, I think we can get our images in here. Let me just check. Coming back to PyCharm. Yep, we have our images. Coming to detect, and then this is the detection log. If I open that, you see that it detects zebra with 0.74%, which is amazing. It's great. Look at that. Well, it doesn't do anything good in here, and also in this case, but in here it can detect tomato with 34% of accuracy, 74% of accuracy detecting another tomato. It fails to detect this tomato, but it does detect these tomatoes and another tomato. I don't know why we are getting all the tomato classes in here, but anyway, we have to wait for a while. You see that it's detecting these tomatoes as well, but it's making a mistake when it comes to detect this as a tomato. The model think that well, the color of this is kind of yellow, and it's a mango. I guess that's why the model is making a mistake. even as a human being, we are going to make a mistake if we see an image like that. But anyway, we can improve the model. I mean, we can do something. And by the way, we used a very small size of the data set, and we use the medium size of the model. Of course, if you use the large model with more data and then give it a context, like in here, if you give it a more context that this kind of situation is tomato, then the model certainly perform well. Those kind of improvements are out of the scope of this video, but certainly I will add a video about optimizing the model and how to improve the accuracy of the model. So let me just check this again. Are we getting more images here? We have yeah, we have mango, zebra, and a lot more. Let's come back. Yep, so if I check this one, the model fails to detect this. Again, this one, and in here we have mango, and so on. Yep, that's it for this video. Thank you for watching. I hope it's helpful and I hope you like it. I made it by heart. Please subscribe to my channel and write down any comment, objection, or suggestions that you would have. Also, please give a thumb to my video. I will appreciate that. Thank you so much for watching.